In March this year, many Claude Code users began to complain that their agent felt dumber than before. Now, this has been a common, timeless, and unprovable complaint, the they don't make things like they used to of the AI world, if you will. But in early April, a 4,500 word GitHub post changed all of that. Stella Laurenzo, a senior director of AI at AMD, came with receipts. She used data from almost 7,000 Claude Code sessions to comprehensively demonstrate the agent's regression. In fact, her work was so compelling that it led to an Anthropic investigation and a public report detailing their findings and fixes. This story is really instructive, so let's follow the data, her conclusions, and then how to build a similar early warning system for your own agents, so that the next time something like this happens, you're not flying blind. We all love a good detective story, whether it's Sherlock Holmes, Nancy Drew, or Detective Pikachu. My favorite part of Lorenzo's analysis was that she figured all of this stuff out from the analysis of local session logs produced by Claude Code. Across 3 months, the AMD team had logged 6,800 sessions, 17,000 thinking blocks, and over 230,000 tool calls. She broke this data down into periods that she called a good, transitional, and degraded. For simplicity, let's talk about the stats across 2 of those periods, the good and the degraded. Between those two, the agent's read activity to edit activity ratio collapsed from 6.6 reads per edit during the good period to just 2 during the degraded period, meaning that on average, the agent was fact gathering 70% less often before making changes. And she had plenty of other stats too. The post also demonstrates that edits without any reading, circular loops, and premature stopping all occurred significantly more often than before. And it wasn't just quantitative stats either. Qualitative metrics like manual user interrupts rose sharply, and Claude began describing its own in-chat work as lazy, rushed, or sloppy. And to top all that, as the output quality went down, their token usage went up, way up in fact. Between February and March, she estimates that the daily usage in tokens increased by a factor of over 100 for a similar number of prompts. Now, to be fair, there are mitigating circumstances. It wasn't just the agent using more tokens by itself. She explains that some of the token increase was due to very excited engineers spinning up further sub-agents. But the result was still pretty bad since they were now trying to do more with degraded agents. She sums up the change from an engineer's perspective, going from I can run 50 agents and they all produce excellent work, to every single one of these agents is now an idiot. In fact, she found that thinking blocks were about 70% shorter in the degraded period than the good period. This is really important because, as she points out, the model being able to spend tokens to think deeply is key to solving these complex problems. Although they had no way of knowing why, this was amazing detective work to prove degradation of Claude Code during this period. Reading her post made me very curious about my own agents. Would I even know if their behavior ever changed? How will I achieve my dream of delegating my work to agents and spending more time gaming if I can't even do that? So I decided to take a look. One experiment I ran was to build a reverse proxy that sits between my coding agents and the model, so it can parse the traffic and ship everything to Elasticsearch. I pointed it at a few different harnesses doing the same task and started poking around. Within one day, the data turned up something really surprising. 2 harnesses with similar token usage on the same task had vastly different bills. One was costing almost 3 times as much as the other. That seemed so odd that my first thought was that I had messed something up. But an online search led me to this GitHub pull request flagging a prompt caching bug in OpenCode. And the behavior matched. Under certain conditions, OpenCode could miss the cache, which means slower inference and dramatically higher cost, exactly what I was seeing in the data. Look, you're not always going to find little gems like this, and I was probably quite lucky here to come across a bug in my tiny demo for a video. It's like buying a Lego dinosaur and finding a real fossil inside. It shouldn't really happen, but I'll take it. Now the point here isn't the bug. Bugs are a fact of life, and I still think OpenCode's amazing. But it does make me wonder, what else might you find if you looked? Now, a bespoke proxy isn't great for production. You're running a separate process, adding a network hop, managing certs and auth. And the proxy itself needs to be maintained, which isn't trivial even when vibe coding. In some ways, especially vibe coding, but I digress. The deeper problem is conceptual. A proxy sits between the harness and the model. It can see the traffic, but it has zero visibility into the harness. Internal state, tool execution details, error handling, all of these things are invisible. You're still treating the harness as a black box. What you actually want is instrumentation inside the harness, and that's where OpenTelemetry comes in. OpenTelemetry, or OTel, is a standardized observability framework for emitting traces, metrics, and logs. The major coding agents like Claude Code, OpenAI Codex, and Gemini CLI have first-party OTel output built in, and others like OpenCode and Pi have plugins or extensions for the same thing. The good news is you don't have to be an expert to set this up. I was able to wire up my coding agent's OTel extension using the docs and Elastic agent skills in less than an hour so that all usage data is sent to this Elastic instance. And this is my resulting dashboard. Let's view it through the lens of which parts of this dashboard might have caught the degradations seen by Laurenzo. At the top, I've got the global usage stats, sessions, turns, tool calls, and failures. Useful as a baseline, but I think the next parts are even more meaningful. This panel shows stop reasons over time. So did the turn end on a tool call? Did the model finish naturally? Or did I manually stop it? A spike in this last category of manual stoppage is exactly what AMD would have seen as engineers saw the model doing the wrong thing and yanked the chain. Now, the read to edit ratio reduction was a key stat, as you remember, and this chart shows exactly that. We also have a chart that breaks down tool calls by type alongside the read to edit ratio over time. So if something changes, whether it's the model, the harness, the server-side update, or so on, I'd expect this ratio to move. And here, I've got tool outcomes over time. So if something starts breaking tool calls, a model regression, a flaky plugin, new permission setup, what have you, the failure rate should climb here. And I also track the tool call patterns so that if a tool isn't being called when it should, or if its data usage patterns change, I'll see those here. And the nice thing is, the dashboard doesn't need to be perfect straight away. That's the beauty of having the underlying logs and metrics in Elastic. I can build whatever dashboard I need later and run any in-depth analysis on the raw data when I notice something is off. The point is that this gives you a real-time display. Look, streaming a dashboard isn't going to win a lot of viewers on Twitch, but it's probably more useful than yet another gaming channel. If a model update shifts behavior, if a server-side cache bug degrades context, or if a harness update changes defaults, I should see it in these trend lines. Before we move on, I'd love to know what you thought about these dashboards, what's good, what's bad, or what's missing. I'm also considering videos on setting up telemetry for major harnesses like Codex or Claude Code, so I'd love to hear from you, which will help us plan these. And on the way to the comments, give us a like, it'll help to keep me employed and help others to find these videos. But let's come back to where we started and close the loop on Laurenzo's story. Just under a month after her post, Anthropic published their report. It turned out that multiple things had changed simultaneously. One, the harness had changed. The default reasoning effort parameter went from high to medium, which affected a lot of people. Two, the new Opus model introduced something called adaptive thinking, which lets the model decide its own thinking budget. This is a great idea for efficiency, but it had a side effect of sometimes deciding not to think at all. Three, and probably the most significant, was a server-side bug. Anthropic had introduced a caching efficiency feature that would discard all thinking blocks on resumption after a month. But this bug meant that once this feature was triggered, it silently dropped all thinking blocks from subsequent message histories. And without the thinking blocks, the model just didn't have enough context while missing the cache, which both degraded performance and increased cost. From the user perspective, these all happened at similar times with little visibility. I can imagine it being a frustrating experience for everyone with little proof that something was even wrong. Except, of course, for Stella Laurenzo. The difference between her and everybody else was that she looked into the logs, performed rigorous analysis, and identified what was going on. Now, up until this point, I've been telling you how wonderful logs are, but of course there are some trade-offs, so let's talk about that. One, session logs generate real data, and retention costs money. As always with observability, you should keep an eye on the volume your team is generating and decide what to log and how long to keep it for. If Timmy over there in your team is constantly spawning 50 sub-agents for a random side project that runs all week, or using OpenClaw to troll Redditors, maybe that doesn't need as much retention as the data from agents working on your company's main product. 2. Real risk of leakage. These logs can capture confidential information and credentials and become yet another potential attack surface and liability. So make sure that you don't create any more risks than you have to. You could exclude message bodies, log metadata or metrics only, or have custom sanitization logic. None of these are perfect, but you should see what makes sense for you. When building these demos, I saw my agent execute shell commands with credentials right in them, which would not get redacted and end up in the logs. I should shamelessly plug though that that's another reason for going with a proven product like Elastic with great granular security and access control. 3. This gets set up but never looked at again. Build a habit of looking at it and set up alerts on the signals that matter to you so you don't have to manually look at them all the time. The lesson for me from all of this is that every session generates signal. Right now, your agent is making decisions you can't see using a harness that grows more complex all the time, shaped by server-side parameters thousands of kilometers away from you. And unless you're capturing that signal, you're really flying blind. OTel support is built into the major harnesses or just one plugin away. And Elastic gives you somewhere secure and easy to use to send it, monitor it, and investigate it. Your coding agent is a black box, but it doesn't have to stay that way. Thanks for watching. I read every comment, so please let me know if you have any questions. Like I said, give us a like if you can, it helps others to find our video. And if you didn't like it, that's fine too. If you let us know why, that'll help us improve. Thanks for watching, see you next time.